Right, sorry. Before even starting, I need to start something, a program that I will show you the output of this program right at the end. But because it takes some time to run, I'd rather run it first, right now. Good. Let's start. I'm a bit absent-minded. Okay, serial talk. You knew this would happen sooner or later. This is a short appendix to my talk from yesterday. I gave you a talk on machine learning. When I ended on a sour note, saying, okay, but this doesn't look like it's relevant, okay? This is machine learning, this is what it looks like. Linear regression, all very cool, but how does this relate to the really cool stuff like computer vision, for example? Okay, so to recap briefly, we saw how you have a bunch of data, you can approximate data with a line, and that's called training. You find the line through an algorithm that is called the gradient descent, and then you use that line to infer data in the future, okay? And now the point is, how do we go from there, this linear regression plays, all the way to something like computer vision? This is going to be very high level, not as detailed as yesterday, much shorter also, but I hope to give you a sense of how we can move from here to there. Okay, so let's start. First, we had reservations and we had pizzas. I actually got a formal complaint from Pat because I pronounced the word pizza strangely, which is probably the only word that I can pronounce properly. So, it was ridiculous. Like, I couldn't understand what you were saying. So one thing in this problem that you won't see in real life problems is, in real life problems, you generally don't have one input variable. Right? Interesting problems have multiple variables. Otherwise, you don't need to build software for it, probably, to be honest. So you have something more like this. You have multiple things that all impact on the label, on the output of the system. You might have the number of pizzas you sell might depend on the reservations, yes, but maybe also on the temperature. Maybe if it's warmer, there are more hungry people around the city, or the number of tourists. For example, let's say that we got this number on a 1 to 10 scale from the local tourist office website, okay? So what happens if I have multiple X variables, multiple input variables? One thing that happens is that where we had an array earlier on as an input, now we have a matrix, right? A matrix where each line is an example and each column is one of the input variables. So what happens mathematically in our system? Well, so far we had one input variable and one output variable, so we could draw this 2D chart, we could draw a line to approximate these points, and then we could use, you will remember, the equation of the line to estimate the number of pizzas. If we add one variable, then we cannot draw a 2D chart anymore. Now we have to draw a 3D chart, right? Reservations, temperature, and, for example, and the pizzas. Which means that our data points are distributed like a cloud in this 3-dimensional space. So to approximate these, I don't use a line. I use the equivalent of a line with one more dimension, right? I use a plane to approximate this stuff. Which means that mathematically, I go from here to the equation of a plane. That is like this, okay? Now we have two axes, x values. X1 and X2, I call them, or reservations and temperature, whatever. And I also have two weights, which makes sense because the weight of reservations, the effect of reservations on pizzas sold is probably not exactly the same effect as temperature of pizza sold. So I need as many weights as I have input variables. If I keep adding input variables, I keep adding dimensions. Now I cannot draw a 4D chart anymore. So here is a picture of my head exploding. But the idea mathematically is exactly the same. I just keep adding x3 and w3 weights and input variables. Okay? So I have this equation. There is one thing that now sticks out in this equation, and we would like to get rid of it. That b, the bias, is now a special case. Everything else is uniform, right? While b is just annoying. We need the special code just for b. So let's get rid of b with a programming trick. We can go back into the data and just add another column, which we call the bias column, that is full of ones. You might see where this is going. I have a b there. I put it first this time instead at the end of the line, okay? And that b can be multiplied by a weight, is multiplied by a weight, as long as that weight is 1. It's just a cheap trick. Essentially, now I can write this. I can call it W0 instead of B, and I multiply it by 1, and it's the same thing. So essentially, now I have a very uniform, very nice equation that is called the linear combination of the weights and the input variables. And the good news is that the linear combination of weights and input variables, I can do this with one line of code with a mathematical operation that is called matrix multiplication. So essentially, I can write this. My inference becomes, you have a matrix, X, all the input variables, and then you have another matrix, and it looks like an array. Let's say that it's a matrix with a single column of weights. Let's just multiply them. What you get is that linear combination. Okay? Once again, in this addendum to the talk, you don't have to understand every step. It's not important. I just would like you to get the feeling of moving on to more and more complex problems. And the feeling you should get is, hey, this is not hard at all, actually. We didn't end up with more complicated code. We ended up with actually somewhat simpler code. So now we moved from linear regression to this other place that is like linear regression with multiple variables, which is called the multivariate linear regression. I think I spent more time on this slide than I hope you appreciate my lame artistic efforts. Okay, second step now. Second step is let's change this time. Let's change the labels, because this problem with pizzas is, of course, fun and interesting, but most really interesting problems are different. They are, first of all, they are not continuous. Here I can have any number of pizzas, right? Even fractional pizzas. While most interesting problems are discrete. Is this the picture of a cat? I don't want to hear 42.2. No, it's either a picture of a cat or it isn't. So I would like to make this work with discrete labels, in particular with binary labels, like this. Did I break even in my restaurant on this particular day or not? Okay? And you might think, okay, what's the point of this? I can just keep using linear regression. And just, for example, round the result. But actually I can't. And the reason why I can't, because obviously if I place this data on a chart again, maybe just the first column and the break even to make it easier to draw the chart. And this is what I get. Right? How am I supposed to draw a line to approximate that stuff? That is not good for linear approximation anymore. So here is another way that I can fix this problem. I can look at my current inference, the linear combination, and I can come up with another function, okay? This is mathematics, so, it's like functions are like violence. If you are not solving the problem, you need more of it. So I come up with another function that I apply over this function so that I can take these results, this number, which can be any number, positive or negative, and I squash this number into the range from 0 to 1, which is the range that I want my label to stay in. So this range, okay? I can have any number, negative or positive, and I want to output something that is either 0 or 1. So I need a function that does this. And I would like to have a function that is not, it doesn't have steps or sudden cliffs. Why? Because I want it to be smooth. Why? Because ultimately I'm using this function to calculate the loss, and I'm using the loss to do gradient descent. And gradient descent doesn't play well with cliffs and holes and discontinuities. Okay? So I would like it to be smooth like this, essentially. This is a known function, or rather one of a family of known functions that is called a sigmoid. And actually, the code that I need to come up with this is, again, a one-liner. So this sigmoid method has the first line that calculates the linear combination, and the second line that just applies the sigmoid to it. Boom, now we have values ranging from 0 to 1. There is one last wrinkle about this. You might remember the loss from yesterday, okay? The loss and the gradient of the loss. Now it's even simpler because we got rid of B, so the gradient is a one-liner as well. You might remember it looked like this. The problem is that once you add the sigmoid to the recipe, I like cooking metaphors in general. At this point, the loss changes to something more like this, which frankly sucks for linear descent. You see all those holes, those cliffs. Those are local minima. Those are places where gradient descent would get stuck. If we get into such a hole, we won't be able to walk out of it. So we have to use another loss. Textbook to the rescue. We can look up what people did, and there is indeed another loss that is called, these are the old ones. We can replace them with this other one. This is called the logarithmic loss. It's not particularly more complicated than the previous one. And that's its gradient. Okay? I won't go into the details because I don't have the time. I will just show you how beautiful and smooth this thing becomes. I didn't invent this, but I will take. Okay, so now we moved on from here to a place that is called the logistic regression. It's not a linear regression anymore. Logistic is statisticians speak for Boolean, if you wish. Again, statisticians in the room, that's not actually precise, but you know, you are in the minority. Okay. So, but now we are not yet into the fabled land of computer vision. We have to cross the terrible forest of drop bears and the cliff of killer jellyfish there, okay? So let's do that. Computer vision. This is a Wikipedia page describing the MNIST database, which is a standardized database of handwritten digits categorized for the specific purpose of being a benchmark for computer vision programs. If you ever meddled with machine learning, you probably use this. It's almost a cliche, but we like it because it's simple. It's 60,000 of these nice digits. Each one of them, let's zoom in, has been carefully centered, scaled to 28 by 28 grayscale 1 byte pixels, and labeled with the value of the digit. Okay? And then there are 10,000 more digits in a test set that I can use to actually find out whether my machine learning program is actually learning. How do I turn this thing into something that we can feed to our logistic regression pizza for break-even forecaster? This might look like quite a large conceptual level, but it's not. Let's just take this thing, squash it into a single line of pixels. 28 per 28 plus 1, if we wanted that. You might remember bias column, which means 785 pixels, all in a row, each pixel is an input variable, from 0 to 255, okay? Which means 60K rows of this thing. This is now our input matrix. Some of you might be puzzled by this. Aren't we destroying the image by squashing it? Aren't we losing all the geometric information in the image? Yes, we are. And indeed, there are algorithms that do not lose that information. They are called the convolutions. They are way more effective with images. But my point is, even just plain old statistics works here. The chances that a given pixel has a given color related to what kind of digit we're talking about. This is enough to get decent results, not great results. Then we have the label. Now I must be a bit hand-wavy. Now I must run a bit because I don't have much time. But again, to give you an idea of how this all works. How do we encode the label? We might say, okay, let's just have 60,000 labels, right? But actually, if you think about it, in our logistic regression program, we had binary values, 0 and 1. Here, we have 10 possible digits, 10 classes, as the express would say. So how come we encode 10 classes where earlier on we had only 1 or 2 classes, a binary value? Well, we know how to build a binary classifier, right? Something with binary values. We have 10 classes, let's just have 10 of them in parallel, which means that the output itself is now 10 columns. Each of these columns contains either 0 or 1, depending on whether this is that specific digit. So for example, for this one, you have all zeros except a single one in the 5th position to say this is a 4. And we do this for all the lines. Again, just giving you the feeling of this. This is called one-hot encoding, because only one element into each line in this matrix is hot. This also means, in case you are wondering, that when we do inference, we will get 10 values instead of only 1 value. What do we do with them? Well, each of those values is going to be something from 0 to 1 excluded, the output of the sigmoid. Those are, in a sense, the confidence that this machine has that we're dealing with that specific digit. How confident are you that this is at 0? 0.029, not very confident at all. We just take the largest one, okay? This one in this case, 0.37. This might well be a 4, okay? We just take that one, and that's our inference. Finally, last piece, the weights. I told you so far that we have 1 weight per input variable, which makes these 785 weights. But now we have 10 classifiers. Multiply it by 10, and that's our matrix of weights. And now we're starting to get close to 10,000 weights. You see how just adding dimensions to the problems make it able to space out into vastly more complex problems. And the result of this is this program. A program that, sorry, MNIST classifier, yeah. I should have opened this, I apologize. Okay, I will make it a little bit bigger so that people in the front lines can see it. Inference. A program that looks very much like the linear regression program we had yesterday, with a few differences. Inference looks much harder, but actually all it's doing is that selection of the maximum number amongst 10 possible results, okay? So this Python code sucks, honestly. I probably should have been working more on this, but I didn't see any reason to make it look nicer. that's what it's doing. It's making an inference and selecting the highest value there. The sigmoid, you have seen it. It does a linear combination, then it applies the sigmoid function over it. The loss and the gradient are the logarithmic loss that we've seen before. This method that used to be called find best line is now called train properly, and it basically didn't change at all since linear regression. Yeah, now it's building a matrix of weights, but otherwise it's pretty much the same thing. Finally, step one of machine learning. Train. Here is the data. Here are all the images. I wrote a very short MNIST library to load the images. That's outside the scope of this talk. And find W, which is now a matrix. The matrix of weights that allows you to make inferences. Then make such an inference. It's here, okay? And then this other code is just looking at the test data. It's because we're making the inference on the test data, we end up with, we have 10,000 characters in the test data set, we end up with 10,000 inferences, and then we check the percent of those inferences that are right by comparing them with the labels in the test data. The reason why I show you this code is that I want to brag about how short the entire stack is, okay? Now, I can make it way shorter. For example, the loss method, we don't really need it. We just need the gradient of the loss. And here, this stuff, I could probably inline a few lines of code. I could inline functions, and I could just print out this thing. Okay, this could easily get below 20 lines. Even like this, it's quite short. And if you look at it for a while, even if I kind of winged it, you can probably understand every single line. Okay, make sense of every single line. These close to 20 lines of Python code are able to recognize handwritten characters with a precision of over 90%. And that is, I hope, proof of how you can move on from linear regression to computer vision in just a few lines.